Hi and welcome again to my Physics Online video lecture supplement series. In today's video I'm going to begin the next set of lectures which covers electrical capacitance and dielectrics. In today's particular video I'm specifically looking at capacitors and capacitance. Capacitors are electronic devices that are used in many types of circuits. They're one of the most fundamental basic elements of a simple electrical circuit. That's not to say that they are necessarily involved in any electrical circuit, but simply to say that a capacitor is one of the basic elements that can be found in a circuit. And what a capacitor basically does is it stores charge. It consists of a pair of conductors which cannot touch each other, and therefore each of which can store some charge. One conductor will store charge that's positive, the other will store charge that's negative. And they're used for a variety of purposes, from tuning radios to trying to eliminate sparking in automobile ignition to timing for your windshield wipers. And they are also used often to store electrical energy that can be discharged very rapidly. So for example, in a lot of high power, pulsed power applications, there tends to be large capacitor banks to store energy to generate whatever large amplitude pulse is being generated. So to get at an actual definition for capacitance, we begin by considering two conductors which are oppositely charged, a positively charged conductor and a negatively charged conductor. And they have to be spatially separated so that they are not physically touching each other, so that the charges from this cannot move to this or vice versa. Then if these conditions are met, there's going to be a potential difference delta V between the two conductors. And that is simply, you can get that from going back and looking at the definition for electrical potential. For example, if these two represented point charges, you could see that there's going to be a potential difference for a third test charge to be moved from here to here. The charge on each of these two conductors is going to in turn be linearly proportional to the potential difference between them. So the more charge that you build here and the more charge you build here, the greater the potential difference is from here to here. In other words, the more work gets done by moving a positive test charge from here to here. The potential difference between the two is linearly proportional to the charge on each of these, which means that it can be written by some equation that looks like y equals mx plus v. And the proportionality constant, the equivalent to the slope in that equation, is called capacitance. And so it has units of farads, where a farad is 1 coulomb per volt, and therefore capacitance is defined as the amount of charge per the potential difference between the two conductors. So it's the amount of charge stored on the surface of either one of the two conductors divided by the potential difference between the two. Now notice that for a pair of parallel plates, which is the simplest type of capacitor, there's going to be plus Q on one plate and minus Q on the other plate, which means ultimately that the total charge stored on the capacitor itself is 0. However, we usually define the charge stored on the capacitor as being essentially how much charge is stored on one of the two plates. So there's plus Q charge on this plate, there's minus Q charge on this plate. So we'd say that this capacitor stores a charge of Q, even though the total charge is actually 0. Now the parallel plate capacitor is in fact the simplest of all capacitors that we can design. And it basically is, the name of the capacitor really describes the type of capacitor that we're dealing with. It consists basically of two plates, which are each has an area. Each one's sort of rectangular like these, although they could be circular or whatever. It could be any geometry you want. The two areas, however, are the same. So this plate and this plate have the same amount of area, and they are parallel to each other. So they are separated by some distance d, and that distance d is the same between any two facing each other points. So these two corners are by d, these two are by d, these two are by d. Middle of this and middle of this is by d, middle of this and middle of this is by d, center of both is by d, etc. And one of the two plates, therefore, if you hook it up to a battery or some other charge supply, is going to end up holding a positive charge, and the other plate will end up having a negative charge. So in this simple circuit that we've constructed, you'd have electrons pulled off of this plate and moving along this wire to the positive terminal, which means that electron holes, move along this wire until they pool up on this plate. And then from this plate, you have electrons passing out along this wire and depositing on this plate. And so if you want to know what is the capacitance of the two plates, you can obtain it from the area and the separation distance. So if they're separated by a distance d, they have an area of a, then the capacitance is going to be given by 1 over 4 pi times the Coulomb constant times a over d, the area over the distance separated. This is also, of course, equal to the permittivity of free space epsilon naught times the area of one plate divided by the distance between the two. Now, to see how that is so, consider the following. So we know that the capacitance is defined as the charge per unit of potential drop between the two plates. But we also know that if you have a pair of parallel plates, that the electric field between the two plates is a uniform constant field. Or at least it's a uniform field and constant, assuming that no charges are added or removed with time. So E of x could just represent E as some constant. So it's constant here. And therefore, if you have a distance between the two plates, delta x, or d, we can actually derive this relationship that the capacitance for a pair of parallel plates is given by the area over the distance times the permittivity by starting from the definition for capacitance. And to this end, I've drawn a pair of parallel plates here and drawn the electric field between them. And basically, as long as you are not near the very edge of the pair, meaning most of the space in between the two, the electric field not only is constant, but we can treat this pair as if each one represents a single infinite plane. So an infinite plane of charge has an electric field which is given by the charge per unit area divided by the permittivity of free space. And so recall that sigma is defined as the charge per unit area. This means, by the way, that the charge can be rewritten as sigma times area. Finally, for a uniform electric field, delta V over delta X gives E sub X. And so in the context of this drawing, where D is the distance between the two, delta V over D is equal to whatever the electric field strength is, and therefore delta V can be rewritten as E times D. And so that is sigma over epsilon naught times D. And Q is therefore Q equals sigma A. So if we plug in this for the delta V and this for the Q, we end up getting C is equal to sigma times area divided by sigma over epsilon naught times distance. And so you can see that the sigmas cancel, and you're left with that the capacitance is epsilon naught times area divided by distance. So we have now derived for this simple pair of parallel plates this relationship between capacitance, area, and distance. Now let's look at a few short examples with this. So here we have a pair of parallel plates, and the question is, what's the capacitance of this pair of parallel plates given that you have a capacitor that stores a charge of 1 coulomb when it's hooked up to a 12-volt battery, meaning there's 1 coulomb here and minus 1 coulomb here, and the battery is 12 volts that is hooked up to this. Alright, well, since C is equal to Q over delta V, we can get the capacitance by noting that this right here is also going to be the voltage drop across the capacitor that's hooked up to this battery. So we have 1.00 coulombs divided by 12.0 volts, and therefore the capacitance of this thing is 1/12, or in significant figures, 1 divided by 12 gets us 0.083333 repeating. So we could write that as 0.0833 farads, and that's the capacitance of this capacitor. Okay, next couple examples. First one is, what is the capacitance of a pair of parallel plates which are separated by 0.1 millimeter and each of which has an area of 1.00 millimeters squared? Alright, so now we can use C is equal to epsilon naught A over D, where A is going to be this area that we were given here, and D is going to be this separation distance right here. So the area is 1.00 millimeters squared. That's also 1.00 times 10 to the 3 times 3, or 3 plus 3 is 6 meters squared. So this distance right here, distance is 0.100 millimeters. That's also 1.00 times 10 to the minus 4 meters. So therefore the total capacitance is going to be given by the permittivity times the area divided by the distance. So that gives us basically 8.854 times 10 to the minus 12 farads per meter, which, by the way, farads per meter is an alternative unit for epsilon naught, so you can figure out how epsilon naught's units work a little more nicely than with the whole newtons times meters over coulomb squared thing, or coulomb squared per newton meter squared. It's easier to say farads per meter. So 8.854 times 10 to the minus 12 times 1 times 10 to the minus 6, or up to 10 to the minus 18, and then divided by 1 times 10 to the minus 4. That gives us a capacitance of basically 88.5 in terms of femtofarads. So little f, big F. This is the same, of course, as 8.85 times 10 to the minus 14 farads. You'll notice that most of the simple capacitors you find, and especially most simple parallel plate capacitors that you find, actually have very small capacitances, as in that example. They may not be picofarad levels, but usually you're going to find that your capacitors are in the pico or nano or sometimes microfarad levels. Very large capacitors might be in the milli or even single farad levels. To figure out why, we could ask how large would the area of the plate need to be if the capacitance is going to be 1 farad and the plates are going to be 1 millimeter apart. So how large of an area are we going to be talking about for each of these plates? Alright, so we begin with C equals epsilon naught A over D. We're solving for the area, so area is C times D over epsilon naught. So that means 1.0 farads times the distance was 1.00 millimeters, so 1.0 millimeters, so 1.0 times 10 to the minus 3 meters divided by 8.854 times 10 to the minus 12 farads per meter. So what does that give us? Well, a quick calculation shows that if you have basically 0.001, you're going to divide by 8.854, you'd end up with this number, and then we're multiplying by 10 to the 12. So basically you end up with an area of approximately 1.13, or I guess we only had two significant figures, so maybe we should say that the area is 1.1 times 10 to the 8 meters squared. And just as a fun kind of aside for comparison, I've pulled up the Wikipedia page on Dothan, Alabama. Now you may be wondering, what the heck does Dothan, Alabama have to do with capacitors? Well, let's scroll on down here, and you can see that it gives what the city's area is, and you can see what the city's land area is here. So if we pull open a calculator, and we note that there's 89.4 square miles, and we decide we're going to convert that thing into meters. So multiply by 1600 and square that. You get this number. And now, just for fun, I'm going to divide that by 2. And what you get is this number right here. This is basically 1.14 times 10 to the 8 square meters, if you look at this guy. Why did I divide that thing by 2? Well, remember that in a parallel plate capacitor, you have two different plates. So this is the area of one plate. The area of both plates would be 2.2 times 10 to the 8 meters squared, which is very nearly land area of Dothan in Alabama. So that gives you a rough estimate of how big would a plate need to be if they're going to be 1 millimeter apart and have a 1 farad capacitance. Alright, so now I want to move on to circuit diagrams. And the reason why I want to do that is because we've now basically covered the first thing that we're going to use in a circuit, which is capacitors, or maybe not covered it, but have seen it and seen a little bit about what a capacitor is. And what we're going to do here is, in the future, we'll be working through a number of problems that involve circuits. And this is true in both lectures, and if you're taking also the lab, you'll see this in the lab. And basically, you have an actual circuit which might look something like this. You've got a battery, you have something that you're trying to power by the battery, maybe you've got a resistor to limit the current that's being drawn or to to alter what the voltage drop is across a given object. And it's kind of cumbersome to draw something like this every time you want to represent this circuit. So instead, we have simple symbols to represent each element in a circuit. So this is our battery, this is a resistor, this is one way of representing a light. Sometimes they draw a circle with a resistor inside of it because these usually create light by sort of having a lot of current pass through a filament, which then glows red hot or white hot, as the case may be. And for a capacitor actually usually is represented by a pair of parallel lines like this, because the simplest kind of capacitor is a parallel plate. So this brings me to two types of combinations for capacitors, because so far I've talked about what happens if you have a single capacitor. Well, you can connect more than one capacitor to a battery. In fact, you can connect, for example, two capacitors in parallel like this, or for that matter, two in series like this. And we'll start with capacitors in parallel, then we'll talk later about capacitors in series. The basic thing is, if you have objects which are in series, then the voltage drop across everything in the series is equal to the voltage drop with the battery. So collectively, the voltage drop across 1, 2, and 3, when added together, will equal the voltage drop across the battery. When they're in parallel like this, the voltage drop across each individual capacitor is equal to the voltage drop across the battery. And this latter principle is actually just conservation of energy. The amount of work done in moving an electron, let's pretend for a second that we don't have either of these capacitors. Maybe you just have a straight up wire connecting the positive to the negative terminal. Well, the amount of work done in moving an electron from the positive terminal to the negative terminal has to be equal to the electric charge times the voltage drop. And the amount of energy gained, or the amount of work done by the battery, the amount of potential energy lost in moving an electron from the negative to the positive, is equal to whatever is this voltage drop times, again, the charge. So that doesn't change if you add elements to this circuit. For example, by adding a pair of parallel plate capacitors, you still have to do the same amount of work to effectively move an electron from this terminal to this terminal, or you gain the same amount of effective energy by moving an electron from this terminal to this terminal. It's just that you do it in this case by way of moving an electron to this plate, kicking an electron off of this plate, which then moves around and hits this terminal. What that means is that we can attempt to treat this pair of capacitors, or any number of capacitors that we want to put in parallel, as if they behave like a single equivalent capacitor. So that's what this diagram right here is showing. There's an equivalent capacitor which has a capacitance that's equal to the capacitance of the first plus the second. So we're going to look at why is that. The first way of approaching this is sort of the conceptual way, which is to say that we've already defined for a pair of parallel plates that the capacitance is given by the area of the plates divided by the separation between the two plates. So suppose that we have a set of capacitors, and we don't really care what the area is for them per se, but they all have the same separation distance between the two plates. Now let's hook them all up in parallel as in this diagram. What does that do? Well, it means that the total area of an equivalent capacitor can be equal to the equivalent areas added together of these three capacitors. So that basically means that the area of the equivalent capacitance in parallel is equal to area 1 plus area 2 plus area 3. Another way of looking at it is that the larger the area is, the more charge you can store on it for the same amount of voltage drop. So by having capacitor 1, capacitor 2, and capacitor 3 all together in parallel, you've increased the effective area of the plates upon which charge can be stored. And so therefore the effective equivalent charge stored is the sum of the charges stored for the 3, the effective area is the sum of the areas for the 3, and the effective capacitance is the sum of the capacitances for the 3. Now the question that you should ponder here is, does this explanation actually hinge upon the separation between the plates being constant for each pair of parallel plates? The answer to that question ultimately is no. It doesn't actually matter that these all have the same separation or not. They can have different separations, and the total capacitance and the total charge stored will still be the sum of the 3 capacitances and the sum of the 3 charges stored. However, it's perhaps easier to use a more mathematically rigorous method for obtaining the same result. And that way we don't have to question, are these actually the same distance apart or not? Does our derivation work or not? Another way of saying what I just said is, if we can show this mathematically true without reference to the separation distance, then the separation distance doesn't actually matter. So here's how we do this. This is dependent not just on the geometry of the capacitors. It's independent of the actual geometry. It could be a pair of parallel plates, could be a embedded pair of capacitors, for example, a wire with a hollow shell wrapped around it like in a coax cable, etc. The capacitance is always given by Q divided by voltage drop across the capacitor. So it's charge stored on the capacitor divided by the voltage drop across the capacitor when the thing is fully charged gives you the capacitance. So it follows that you can rearrange this equation by multiplying both sides by delta V to get that the stored charge is equal to the capacitance times the voltage drop. So the total charge, therefore, for a set of capacitors is going to be Q1 plus Q2 plus Q3. So this is Q1, here's Q2, here's Q3. And this total charge stored on all 3 or more, or 2, capacitors must be equal to the charge that would have been stored on an equivalent single capacitor. So we write that as Q total equals Q equivalent. And the equivalent capacitor also has to have the same voltage drop as the other capacitors because it's hooked up to the same battery. Since the voltage drop is the same across every one of the capacitors that are in parallel, we can write that delta VEQ, the equivalent voltage drop, is equal to delta V1, the voltage drop across capacitor 1, which equals the voltage drop across capacitor 2, which equals the voltage drop across capacitor 3, and so on. So therefore, we're able to write that this is the charge stored on the equivalent capacitor, which is C equivalent delta V. And that has to be equal to the charge on the first plus the charge on the second plus the charge on the third. And since all the voltages are the same, we'll just use a delta V for all of them. We can divide out the delta V from each of these. And so what that leaves us with is that the capacitance of the equivalent capacitor is equal to the sum of the individual capacitances of all these capacitors that are in parallel. C1 plus C2 plus C3, etc. And notice that nowhere in here did I have to make reference to the area of the capacitors or the separation distance between the plates of the capacitors. So it's going to work even if we're not using parallel plate capacitors at all. Alright, the other way that we can hook capacitors up to each other is in series. And if the capacitors are in series, we show the diagram like this. Here's C1, C2, and C3 in series with each other. And in this case, that means that the total charge stored on each capacitor has to be the same. And you can see that because how is it that we get charges on these middle capacitors, or on this middle capacitor, I should say? Well, let's treat this as a battery which sends out an electron this way and which pulls electrons this way off of this plate. The electron that is sent off this way is going to end up accumulating on this plate, which is going to kick another electron off of this plate, causing there to be a hole here. That electron moves here, kicks an electron off of this plate, which moves here, kicks an electron off of this plate, which is the hole that gets drawn to the positive terminal, to the negative terminal of the battery. And so what that basically means is that for each electron moved to this plate, we kick off one electron to this plate, which has to go to this plate, which in turn kicks off one electron from this plate that has to go here, which kicks off one electron here, which ends up going to the other terminal of the battery. Hence, the charge on all these capacitors must be the same. So, the charge is the same. What about the voltages? Well, conservation of energy here requires, instead of having all of these at the same voltage, that if you add the voltage drop across this, plus the voltage drop across this, plus the voltage drop across this, you get the total voltage drop of the battery that they're hooked together to. So we write that as Q total equals Q1 equals Q2 equals Q3 equals etc. Q. So this is the charge on every capacitor. This is the potential drop across the series of capacitors, and it's given by the drop across 1 plus the drop across 2 plus the drop across 3. So since the potential drop across a given capacitor can be written as delta V equals Q over C, this, by the way, comes from C equals Q over delta V. We've just rearranged that. Since this is true, we can therefore get the total voltage drop, because since it's delta V1 plus delta V2 plus delta V3, we can write it as delta V equals delta V1. Here's delta V2, here's delta V3, etc. And this one, in turn, for the equivalent capacitor, could be written as Q over C equivalent. And again, same charge on this capacitor, this equivalent capacitor. So since all of these have the same factor of Q, we can remove the Q, basically divide it out of everything, and we're left with 1 over the equivalent capacitance is 1 over the first capacitor's capacitance plus 1 over the second one plus 1 over the third one's capacitance, and so on. So note here what the implication of these two possible combinations are. Implication 1 is that if you place capacitors in series with each other, you can expect the total capacitance to be smaller than the individual capacitance of the smallest capacitor. If you place them in parallel, then you can expect the capacitance to be larger than the largest individual capacitor that's placed in parallel. We have in fact seen these two relationships before, but in a different context. I've been talking today about the equivalent capacitance for series capacitors and parallel capacitors. Earlier, in a previous set of lectures, I talked about the equivalent spring constant for a set of springs that are either in parallel or series. And you'll notice that for capacitors, if they're in series, you take 1 over the total, and it's equal to 1 over the first plus 1 over the second plus 1 over the third. Well, that's the same thing for spring constants for springs in series. 1 over the effective equivalent spring constant is 1 over the first spring constant plus 1 over the second plus 1 over the third, and so on. Whereas in parallel, the total spring constant is equal to the sum of the individual spring constants, and the same is true of capacitors. So with that said, let's go ahead and look at a few more short examples. So the question is, what is the equivalent capacitance to a pair of identical capacitors in series if each capacitor has a capacitance of 100 nanofarads? All right, these are going to be placed in series. So what does that look like? Well, 1 over C equivalent is equal to 1 over C1 plus 1 over C2. So this is 1 over 100 nanofarads plus 1 over 100 nanofarads, which is 2 over 100 nanofarads, which is 1 over 50 nanofarads. So therefore, the equivalent capacitance for this pair in parallel is going to be 50 nanofarads, which is half as much as the capacitance that we had for each one of these. Again, this is exactly like what happened, recall, if we took two identical springs and then attached them to each other and tried to find what the effective spring constant was. So the effective spring constant in this case was equal to 1/2 of the individual spring constants, since these were identical springs. The next example places the pair of capacitors in parallel. So now we have C equivalent is C1 plus C2. That's 100 nanofarads plus another 100 nanofarads, or 200 nanofarads. Again, this is the same result that we got when we took two identical springs and we placed them in parallel on a given mass. Here was spring 1, here is spring 2. We said this was equivalent to a spring which had an effective spring constant which was twice the individual spring constants of either of these two identical springs. Okay, what happens if we have a set of 3, both in series and parallel? So in parallel, we'll do that one first because parallel is easier to do slightly. We have C equivalent is equal to C1 plus C2 plus C3. And so that's 10 microfarads plus 20 microfarads plus 40 microfarads. And so what we end up with is the equivalent in parallel is equal to 70.0 microfarads. So this is the equivalent capacitance in parallel. What about in series? If they're in series, then the equivalent must be 1 over the first. 1 over the equivalent is 1 over the first plus 1 over the second plus 1 over the third. And so that is going to look like 1 over 10 microfarads plus 1 over 20 microfarads plus 1 over 40 microfarads. And notice that we can rewrite this by saying that, put all of these, in other words, in terms of increments of 10 microfarads. Then we would have 4 plus 2 plus 1 divided by 40 microfarads. And so this obviously is going to give us 7, and so the equivalent in series must be 40 sevenths or 40.0 sevenths of a microfarad, which is of course going to be, if we round off to 3 significant figures, 5.71. microfarads. So 5.71 microfarads is the equivalent in series. So that is our 3 short examples for this part of the lectures. Alright, what happens if we have a little bit more complex of a combination of capacitors? In other words, rather than just putting all of them in series or all of them in parallel, we might have some circuit like this, or some part of a circuit that looks like this, where there's clearly some that are in parallel, clearly also some that are in series. How do we approach it? Well, oftentimes what happens is we look and see, is there a pair of capacitors which are most obviously in parallel with each other fundamentally before they are in series with anything else. So in this particular circuit, if we look at it, you see that this 4 is in series with both the 1 and the 3, and collectively all 3 are in parallel with the 6 and the 2 and the 8. The 6 and the 2 are in turn in parallel with each other, and both together are in series with the 8. Well, the 4 is in series with both the 1 and the 3. The 3 is in series with the 4, but it's in parallel with the 1. The 1 is in parallel with the 3 in series with the 4. So this pair has to be more fundamental than either the 4 and the 1 or the 4 and the 3. So we have to break this one down into something equivalent first. So 1 and 3 are in parallel with each other. That means that what we have is an equivalent of a 4. Similarly down here, the 6 and the 2 are in parallel with each other. The 6 is in series with the 8. The 2 is in series with the 8. We have to do the 6 and the 2 next. So that in parallel gives us an 8. Now looking at this combination, the two 4s are in series, the two 8s are in series. Each 8 is in parallel with each 4. Therefore, we need to break down the 8s and we need to break down the 4s next. So two 4s which happen to be in series with each other gives us an equivalent of a 2. Two 8s which are in series gives us an equivalent of a 4. So now these two are in parallel, so we can just add them up. 4 plus 2 gives us 6. So that's one way of approaching more complex combinations of capacitors, combinations that have both capacitors in series and capacitors in parallel together. I want to move on to talking now about how much energy gets stored in a capacitor. And the way that we do that is that we recall just how much work it is that it takes to remove a small amount of charge from one plate of the capacitor to the other plate of the capacitor. So if we have a small amount of charge delta Q, and we're moving it from one plate to the other, we're also moving it across a potential difference of delta V, and so the work done must be the potential difference times the charge, or delta V delta Q. The potential difference itself is going to be also changing though as you start removing charge, because the potential difference between the two plates is given by however much charge is on one plate divided by the capacitance of the capacitor. So if I remove a delta Q, then I will have lowered the potential difference by delta Q over C. So that means that as we're removing charge from one place to the next, we're also losing not only charge but also potential difference. And we have seen something similar before in talking about work done by a spring. So since voltage is linear with charge, we have a graph that looks like this. Delta V, here's Q, here's our delta Q, and basically the amount of work done is going to be given by the area under this linear curve. And you can see that by noting that the amount of work done to remove any given charge, delta Q, must be equal to delta Q times how much we've changed the voltage by, or whatever the voltage drop is for that charge and moving it from one plate to the next. So this right here then represents sort of one area, and you have a bunch of these areas as you remove all the charge from one plate to the next. That's the total area under this triangle. You can see that zooming in here, that there's a little area above, there's also a little area below. The amount above and the amount below should be equal. This means that the work done by moving a given charge from one to the next might be given by whatever that charge is times the voltage drop, but in moving all the charges from one plate to the other, you end up getting the area under what looks like a triangle here. So that would be the height times the base divided by 2. 1/2 times Q times delta V, where Q is how much charge is initially stored on each plate. Delta V is the potential drop across the two plates. And since delta V can be rewritten, or since Q can be rewritten, this work equation has three different forms that it could take. It's 1/2 Q delta V. It's also 1/2 C delta V squared. It's also 1/2 Q squared over C. And this also gives you the function for the potential energy stored in a charged capacitor. There's one more point that I'd like to mention while discussing the topic of energy stored within a capacitor, and that is that if you write out this potential energy equation, U equals 1/2 C delta V squared. That is, of course, the middle of those three equations that I showed on the slide. We can rewrite this by noting that for parallel plates, you have C equals epsilon naught A over D. We got that equation earlier for the parallel plate capacitor case. The other thing is that for the same pair of parallel plates, we've already obtained previously that the voltage drop between the two plates is equal to the electric field strength times the distance between the two plates. And that's something that we got from the uniform field. So uniform E field requires that E is always delta V over delta R, or if we want E sub x, it's delta V over delta x, or so on. You can rearrange this and then note that delta R is really the distance between the two plates, and that gets you the electric field strength between the two. So if we substitute these two into the equation above, you end up getting U equals 1/2 of epsilon naught times area divided by distance between the plates, and then that's multiplied by E times D, and those are both squared. So there's going to be some term cancellation. We can rewrite this therefore as 1/2 times epsilon naught times E squared times A times D. So notice that this product, A times D, area times distance for the parallel plate capacitors, this is a volume. So that means that we can define a new term, which is sometimes called lowercase u, and lowercase u is given by 1/2 epsilon naught times E squared. This term right here is basically what's called energy density. So that is energy per unit volume. And so this is one of the equations that is useful for how much energy storage you get for the size of a capacitor that you're using. So based on the size of the capacitor, how much energy do you think you can store? This is an equation that's valid for any pair of parallel plates, but this is the energy density equation that we will refer back to this when talking about how an inductor, another element of a circuit, can store energy via the magnetic field. And we'll see that that has an equation that is also kind of similar to this one in general form. Basically, what this means is that the energy density is proportional to the electric field strength squared. So it's time now to turn to a few longer examples that have to do with capacitors, capacitance, and electrical energy storage. The first one that we're going to look at is one that has some obvious biomedical implications, which is a defibrillator. So we're told that the capacitor is storing 1.25 kilojoules of energy. That means that we can write U equals 1,250 joules, and it's being stored on a capacitor which has a capacitance of 150 microfarads. So C is equal to 1.50 times 10 to the minus 4 farads. And then last but not least, this is discharged in delta T is equal to something like 4.00 times 10 to the minus 3 seconds. And then we should note that half of the energy, so delta U is equal to 1/2 of U, which in this case is 625 joules. So the first thing that we're asked is to determine the voltage drop on the capacitor before and after discharging. So we'll label that as delta V initial and delta V final. Alright, so as you know, U is equal to 1/2 times the capacitance times the voltage drop squared. So initially we can write delta V initial is equal to U initial times 2 divided by C, and all that's under a square root. So this gives us, so therefore we can write here that the initial voltage drop is 2 times U, which was 1,250 joules, divided by the capacitance 150 microjoules, or 1.50 times 10 to the minus 4 farads. So throw that stuff into the calculator, and what you come out with is 2 times 1250 divided by 1.5, and then that's divided by another 10 to the minus 4. So that we put in like this and take a square root, and you get 4,082. So since we have three significant figures to work with here, maybe delta V initial is approximately 4,080 volts. Okay, then half the energy is discharged, so delta V final is going to be square root 2U final over 1.50 times 10 to the minus 4 farads. U final being, in this case, 625 joules. So put that into the calculator. We're basically dividing this number by 2, and then we're taking a square root, so that's going to give us a total of basically 2,887. So this is roughly 2,890 volts. So that's what the final voltage drop across the capacitor will be after the discharge. Part B asks us to determine what the total charge was before and after discharging. So we can also use the fact that the energy stored on the capacitor is given by U equals 1/2 of Q squared over C. And so therefore the initial charge should look like U times c times 2 square root, and that's the initial. So that's square root of 2 times 1,250 joules times 1.50 times 10 to the minus 4 farads. So therefore the initial charge that is stored on the capacitor about 0.61237. So 0.612 coulombs. And then after discharging, Q final is again square root 2 U initial C, which is square root of 2 times 1250 joules times 1.50 by 10 to the minus 4 farads. And of course 1250 over 2 is again 625. So that means that the total charge finally will be about 0.4. QF is about 0.4330 coulombs. Okay, so then C, determine the average power delivered to the patient. This one we don't necessarily need to make reference to the capacitor itself, but it's a nice review because power, the average power, is the amount of work done per unit time. So work per unit time, which is also change in the potential energy per unit time. So that is basically 1250 minus 625, which gives us 625 joules divided by the time, 4.00 times 10 to the minus 3 seconds. So that gives us 156,250 watts. So the average power, if we round that off, is basically 156 kilowatts. So that is the average power that's actually delivered to the patient. Finally, suppose that the capacitor has a known thickness, like say 15.0 micrometers. We want to know, therefore, what is the energy density that this capacitor is storing. So, as you know, U, the energy density, is 1/2 epsilon naught E squared. But how do we get that? Well, E is given by the change in voltage per unit distance. So we'll call this, let's say, a delta X. So this right here represents delta X. And then we need somehow to figure out, well, this would work. We can do it this way. The other way we could do it is that we could figure out the energy and divide by the volume. So alternatively, we could say, or U equals big U divided by the area times the distance. You'd have to find this area somehow, but you could get that from using C equals epsilon naught A over D. And so the area, therefore, is equal to C times D over epsilon naught. So these are the two possibilities. Note that there's actually some additional tricks that can be used to sort of enhance the size, the effective area of the capacitors. For example, they may not necessarily be parallel plates, because you're going to find that this is a pretty large area for something that should be handheld. In any case, either way, this will work. Basically, this one right here, this method now says that U is 1/2 times epsilon naught times delta V over delta X, quantity squared. And so U is equal to 1/2 times 8.8 5 by 10 to the minus 12 farads per meter times the change in voltage, which we found previously to be 4080 volts for the initial condition, and we'll just do for the initial condition. And we're dividing that by delta x, which is 1.50 times 10 to the minus 5 meters. And then that number has to be squared. So what is this going to give us when we do all this? We're going to get 0.5 times 8.85 times 10 to the minus 12 times another 4080 squared times divided by a 1.5 squared, and then divided by 10 to the minus 5. So that would be the same, squared. That would be the same as dividing by 10 to the minus 10. And so what we end up getting here is 327,379 joules per cubic meter. So little u is 327 kilojoules per cubic meter. That's how much energy is being stored initially by those capacitors, and we could also figure out how much is finally given the final voltage, but I'm not going to do that here. For the next example, I kind of wanted to do something a little different. We've been treating capacitors like they're parallel plate capacitors all the time, but of course there are other geometries that work for a capacitor. For example, this geometry would give us a cylindrical capacitor. Maybe there's a negative charge stored on the outer ring, and then there's a positive charge on the inner cylinder. This, by the way, looks kind of like what a coaxial cable would look like. So these things are obviously, they do exist. Let's try to figure out what the capacitance is of this cylindrical capacitor based on the geometry given here. Inner radius of A, outer radius effectively being B. Remember that this is a thin conductor. In any case, if the whole thing is neutrally charged on the net, all of the charges should appear on this inner surface and then on this outer surface, since these are conductors. So the outer surface of the inner guy, the inner surface of the outer guy. And so here are the dimensions that are relevant. A, B, thing has a length L. Here is R, which we can use to describe, for example, a Gaussian surface if we want to figure out what the E field is in here. And then Q is the charge stored on each. Alright, the first thing that we have to do in order to solve for this is basically, if we want to find the capacitance, we can use C is equal to Q over delta V. So we need to figure out these two terms. And one way that we can go about doing that is we know that if you have a long straight wire with charges placed on it, the field ends up being directed outward like so in all directions radially from the wire. And this we actually worked previously in the video for Gauss's law. You'll recall that we chose the Gaussian surface to basically be a cylinder that surrounds this wire. So what happens if we surround this wire by a second conductor with an opposite charge? Well, the answer is nothing happens. This field stays the same, it just happens to terminate at some point. And the reason for that is that this second conductor you're looking at the inside, so looking from the top, you have a conductor that's like this. If there's minus charges like so surrounding it, then the field lines from those, you'll recall, basically will point out radially from it. But they will not point to the inside of this conductor because of the symmetry of the charge distribution. In other words, if we chose some given arbitrary Gaussian surface, we'll make it an arbitrary cylinder such that it's inside of this outer one, you'll notice that anywhere that you put it, as long as R is less than B, that Q enclosed would be 0 for just this case. And so therefore the flux is 0, so hence flux, which is E dot A, is equal to 0, and this implies that the E field is 0. So what happens when we add this long wire inside of this? Well, basically, then we end up getting a field that points out from the long wire, like so. And this field that is outside ends up basically going away. And so your new field basically looks like this, which is what's drawn in the original diagram. So what was the field that we found for the long straight wire? Well, it was E equals 1 over 2 pi epsilon naught times lambda divided by R, where R is the distance, how far are we away from the wire. So this distance right here represents R. In other words, R could represent the distance to this Gaussian surface in this diagram here. Well, lambda is nothing but Q per unit length. So in the diagram that I originally showed, the length of the inner and outer cylinders was lowercase l. So therefore we have the E field. It's 1 over 2 pi epsilon naught Q divided by R times L. This is E of R, where basically A is less than R is less than B. So again, that's looking down on a diagram somewhat like this. You have your outer negatively charged surface. This is an actually existing outer shell of this pair, and this is negative Q. You have an inner positively charged Q thing here. Here is distance A. Distance B is this, and distance R is to some arbitrary point that is between the two surfaces. Now, the field is not uniform. It's falling off like 1 over R. Therefore, if we want to figure out what the voltage drop is between A and B, we end up basically needing to do an integral from surface A to surface B of the E field, basically E dot dl, where dl in this case is more properly actually a dr, because we're actually integrating from this point out to this point, and this is a radial motion. So E dot dr, basically now what this is going to give us is delta V is 1 over 2 pi epsilon naught L, where L again is how tall the cylinders are, times Q, integral from A to B. E is a radial. We're integrating in the radial direction, so this dot product gives us a cosine of 0, which is 1. and so you're left with a dr over r. So as you know, this is going to integrate to give us a logarithm. This whole thing basically looks like ln r evaluated from r equals a to b. So delta v therefore must be q over 2 pi epsilon naught L times ln of b minus ln of a, which is the same thing as ln b over a, like so. So this gets us the potential difference between the two surfaces. Next, what we need to do is note that the capacitance is given by, since it's C is Q over delta V, and since we found that Q is basically going to be lambda over L, basically this means that the two are ultimately proportional, because you can see that delta V is equal to Q divided by a bunch of constants. So if we take C equals Q over delta V, that basically means we have Q divided by Q over 2 pi epsilon naught L times the natural log of B over A. And so, of course, these two Q's go away, and so the capacitance must simply be 2 pi epsilon naught times L divided by the logarithm, or the natural log, of B over A. And that's the capacitance that you get for a pair of parallel, and maybe we could even say from a cross-sectional perspective, concentric cylinders, a cylindrical capacitor. As a third example, let's try to figure out what the capacitance for a hypothetical spherical capacitor might be. So a spherical capacitor maybe has a geometry like this, where instead of being two cylinders, these are more like two balls that are suspended in each other. It's worth noting here that you could, in principle, make a spherical capacitor, except for that instead of filling the area between the inner and outer ball with empty space, you'd fill it with some sort of insulator, which in this case would function as a dielectric, and that's the topic of our next part of this lecture set. So let's go ahead and calculate what the capacitance for the pair of concentric spheres is. Alright, so I begin with a little drawing of this diagram. The E field between the two charged spheres is going to be given by E is equal to basically whatever is 1 over 4 pi epsilon naught Q over R squared, where R is the distance from the center of the smaller sphere. Basically we have the condition A is less than R is less than B, where B is the outer sphere's radius, A is the inner sphere's radius. And again, note that these two spheres are effectively spherical shells. The thickness of the shell itself doesn't matter. In fact, the inner one could be totally solid because, again, they are conductors. That means that the positive charge that's on the inner conductor's surface, which is on the inner conductor, will exist entirely on the inner conductor's surface. The charge that's on the outer conductor will be entirely on the outer conductor's inner surface. So even if this outer conductor has a really thick shell, or this one is totally solid, the geometry still works out the same. So this, again, also looks like the same kind of E field that would be generated if all of this charge were concentrated in the very center of this inner conductor. You can use Gauss's law to obtain this result. In any case, what we're looking for here is the capacitance, and as you know, the capacitance is going to be given by the charge divided by the change in voltage, or the voltage drop between this point and this point. So again, we need to find the voltage drop, and again, it should be the integral of E dot dl, or in this case, E dot dr. So that basically is going to look like the integral from the inner to the outer radius of 1 over 4 pi epsilon naught times q over r squared r hat dotted with dr r hat, because both the direction of integration and the direction of the E field point in the radial direction. So this basically is going to give us delta V is equal to 1 over 4 pi epsilon naught times Q times 1 over R, evaluated from R is equal to A to R equals B. And so that should give us Q over 4 pi epsilon naught times 1 over B minus 1 over A. Okay, and this can then be sort of rearranged, because this difference right here you can use is A minus B over the quantity A times B. And in fact, I dropped a negative sign earlier here, so we should have a negative sign out here. This whole thing, therefore, is B minus A over AB times Q 4 pi over epsilon naught without the minus sign. So if we want to get the total capacitance, we're taking Q and we're dividing it by delta V. So that's Q divided by Q over 4 pi epsilon naught times B minus A over AB. And so again, the charge cancels out, and we get that C is equal to basically A times B divided by B minus A times the times the 4 pi epsilon naught. And so this right here is the capacitance of your pair of parallel spheres. And an interesting aside is what happens if we allow this outer shell to be very large, infinitely large, in fact. Well, then we effectively are left with one actual conductor. But if you look at the equation here, if we allow B to become infinitely large, then what's going to happen is this term right here will go away. And so you'll end up with delta V is equal to Q over 4 pi epsilon naught times A. And so you can then figure out what the capacitance is by dividing Q by this number, and you get that C is equal to 4 pi epsilon naught times A. So that is the case that happens if B approaches infinity. In other words, if this outer sphere becomes infinitely large. And oddly enough, what that means is that we're going to end up with a finite capacitance for a single conducting sphere. So before concluding today, I wanted to give a brief summary of what all we've done in this lecture. I've introduced the idea of a capacitor and then noted that the capacitance C is defined as the charge per unit voltage drop. From there, we discussed what happens if you have a pair of parallel plates. So the parallel plate capacitor's capacitance is given by C is equal to epsilon naught times the area divided by the distance between the plates. So this is area of one plate. This is distance between plates. And we found from that you would need a very, very large pair of parallel plates indeed if you wanted to have a capacitance approaching 1 farad. So unit of capacitance is farad, and we also noted that epsilon naught has units of farads per meter as a result of this. I noted that if you wanted to build a 1 farad capacitor with a pair of parallel plates separated by only 1 millimeter, that the two plates combined would have an area about the same size as the city of Dothan. So you'd need a very large area in order to be able to actually get a large capacitance. Then we discussed what happens when you put the capacitors in series and in parallel. So in series, you have 1 over C equivalent is equal to the sum of 1 over C sub I. In parallel, you have that C equivalent is equal to the sum of the individual capacitances, and this is basically the same as with a spring. Then we looked at energy stored by a capacitor and noted that the total energy stored is given by the amount of work that it would take to move a single charge from one plate to the other. And that amount of work is given by 1/2 Q delta V, or 1/2 C times delta V squared, or 1/2 of Q squared over C. And we learned a new definition, therefore, which was energy density. And the energy density, lowercase u, is the total energy per unit volume, or per area times distance, or thickness. And that was given by 1/2 of epsilon naught times E squared, where E is electric field strength. So that is a general summary of everything that was covered in today's lecture. And therefore, if you watch back through the lecture, you can try to find each of those points. I basically did that summary in order. I don't have timestamps, of course, for each particular point as I'm recording it, but hopefully you enjoyed this video. I hope actually that the summary is helpful at the end. If so, then I'll try to remember to do that in future videos as well. In any case, the next video is going to be part 2 of this lecture set, which is going to talk about what happens if you put an insulator between the two conducting plates. In other words, what happens if you insert a dielectric into the capacitor. Until then, so long, and thanks for watching.